Okay, so welcome to the Unit 3 essay. So to begin, we're going to talk about how there are two different types of heart cells. So we have our cardiomyocyte and our autorhythmic cells. And so audiorhythmic, that's kind of self-explanatory. That sets like the rhythm of the heart. And so that is going to be, for example, our SA node. And then our cardiomyocyte, that's going to be like the contractile of the heart. So an example of that is going to be the ventricle muscle. And so to show those two different action potentials, I'm going to draw two different graphs here. And then we have and so with our cardiomyocytes, that's going to be a contraction. So it's going to look like this. And then for our audiorhythmic, it's going to look more like this. And that's going to do it all over again. And so now let's talk about the different channels that are involved. And so one thing to note is that this is -60, -90, -40 threshold, -70. And I could have those flipped, but that's what we're going to do for now. And so for this beginning phase right here, we have our IK1 channels, and I means current. And so we're going to have potassium coming in, and then once we hit here, our potassium begins to close, and our sodium begins to enter. And then we'll get our I and A channels. And then so like I said, I is current. And then once we get up to here, we're going to have two different channels, our ITO1 and 2. That's for chloride and potassium. And ITO is our current of our outward transient. That's why we have our ITO. And so those different ions begin to enter this cell. And then we get to this very unique part of this action potential, what we call the plateau phase. And that is due to 4 different channels being opened. And so we have our ICAL. There's 2 different types of calcium. There's L-type and T-type. So we have our L-type, which is slow calcium coming in. And then we have our IKUR, which is our potassium ultra rapid, and then our IKR, which is our rapid, then our IKS, which is slow. And one thing to remember here is that we have calcium that is coming into the cell here, and then we have potassium that's wanting to leave. And so once that potassium becomes greater than that calcium, we're going to have our rapid repolarization right here. And so we have our IK1 channels again. And then we begin all over right here. So we'll have our IK1, and then we'll go up again and then go back down. And I guess this is a good time to talk about calcium in heart cells. And so it's very similar to the heart. or to others like skeletal muscle. And the fact that we have our cell here, and we have DHP and then our SR. And so we'll have calcium that comes in through here. The action potential gets sent to belong. That activates the ICF there, and then we'll get our contraction from our sarcomeres in here. And so 90% in our heart muscle is going to come from the ICF for calcium, and 10% is going to come through the ECF. And so we have these different channels that are still allowing for calcium to enter, which causes the contraction of a heart cell. And so now that we talked about the contraction, let's talk about what sets the rhythm for the heart. And so right here at the beginning, we notice that there's this steady increase in the slope. It's not really flat like we've seen previously. And that's due to these channels called the HCN, sometimes referred to as the funny channels. And so this is where we still have potassium entering, but it's just kind of like slowly leaking in. And that's why we have this steady increase in the cell. And then we have here, which is unique as well, instead of sodium that causes our depolarization, we have calcium. And like the I here still stands for current. And one thing I forgot to mention down here is that we also have our potassium ACH channels and our IF channels that are causing this phase to happen still. And then once we get here, we'll go back and we'll have our potassium, which causes the repolarization of these autorhythmic cells. And one thing is, this is our T-type right here. And so that kind of wraps up our two different types of our heart cells and what their different roles are in the heart. Okay, so for the next part of this essay, we're going to talk a little bit about the EKGs. And so to do that, I'm going to draw a heart here. And so we have our atriums and then our ventricles down here too, to separate those. And then I'm also going to draw an SA node, and then we're going to have our AV node. And so that's the heart. And so now we're going to get into what the different signals are going to do. But before we get right into the heart, I'm going to kind of show what will be an upside or an upright wave and a downside wave. And so let's say we have these cells here. And then up here we'll have our negative and our positive electrodes. And then let's say we get a depolarization that gets sent down. And when we're dealing with EKGs, we're thinking outside of the cell. And so once we get a depolarization, we'll have negative on the outside. And let's say we go the opposite way on this one. And so we get a depolarization. And so I'm going to move this over to draw these. And so for this first one right here, we're a negative tail going towards a positive, we're going to have upside. And then if we have a negative going towards a negative, it's going to be down. So that's important to remember as we talk about the EKG. And so this is our vectors, what I should mention as well. So these are vectors. And so we're dealing with the direction and magnitude of the signal that is happening. And so we begin at this SA node, and the signal gets sent down, and we have our depolarization, and we get a vector that looks like this, and that will cause our P wave. And I'm just going to draw that right here. So we get a P wave. P. And then that depolarization gets going, and then it gets kind of stuck around this AV node here. And then that's what causes what we have our PR interval. And then once we get to the AV node, it's going to branch off. So we're going to have this bundle of his Purkinje fibers. And we're going to have more action potentials being sent. But remember, we're not thinking action potentials because we're looking on the outside of the cell. But it's still going to cause a depolarization. And then we get a vector going out this way. And that will cause this Q wave to happen. And then our signal keeps going until it reaches down here on the ventricle. And then we have our next vector, which is going to look like this. And that's where we get our R wave. And then we have it's getting depolarized more. And so now we have vectors going this way. And then we get our S wave. And then there's a point in time where right in here we have like no net movement. And so we get this ST interval right here. And then once our cells start repolarizing the ventricle, it's going to cause to go this way. And we'll get our T wave. And then it just goes over again if we keeps going through that cycle. And that's where we get our EKG. And so to summarize, we have our P wave, Q, R, S, and then T. So our P wave is going to be our atrial depolarization. And then QRS is going to be our ventricle depolarization. And then our T wave is our ventricle repolarization. And so that summarizes our EKGs. Okay, so now we're going to talk about what an EKG would look like if we had two problems happen in the heart, specifically end-STEMI and STEMI. So to do that, I'm going to draw two different hearts here. I know those aren't pretty. just for both of them, I'm going to draw a normal EKG because we're going to look at the EKG and what those would look like. Okay, so right up here we'll talk about end-STEMI. And over here we'll talk about STEMI. And so end-STEMI is we get these cells that are hypoxic or hypoxia, and those are just damaged cells. And so if you notice, it doesn't go all the way to the end of the heart membrane. And so if we get something that happens to that, our EKG is going to think of it as like a current of injury, and it's going to create a new baseline, which is going to be elevated from a normal EKG. And so that is going to look, so it's going to be elevated, and we're still going to have our P wave, QRS, and let me back up. So it's going to go, and it's going to kind of have like a weird S wave. It's going to be depressed, and then go up there. So it's called ST depression. And so that's what happens with end-STEMI. And then for STEMI, it's worse condition than STEMI, and that's when we get hypoxia cells that go all the way to the end of the membrane. So we still have hypoxia cells. And now instead of the baseline getting changed, it's still going to be at a normal baseline, but it's going to go up here, and then we're going to have our P, and then our Q, R, S. And sorry, I went too far. Because now we're going to have an ST wave that's elevated, so it's going to go, and then we're still going to have that, and then it's going to dip up. And so this is at a different level than it is here. So this is elevated. So this is an ST elevated signal, and that's end-STEMI and STEMI. Okay, so now we're going to talk about inotropy, lusitropy, and chronotropy. And there's this applies to both our contractile and autorhythmic cells. And to begin, we'll do our autorhythmic. And so there's two different receptors that we'll have, our beta 1 and then our M2. Our M2 will want to decrease our heart rate, where our beta 1 will want to increase. And so beta 1 will be activated by norepinephrine or epinephrine, where our M2 will be acetylcholine. And so with our beta 1, we'll have an increase. With beta 1, we'll activate our alpha subunit, which will then do camp. And then that will cause our HCN. And then that will cause an increase in our heart rate. And then over here we'll have L type. Then there's two types. We'll have if we have a steeper slope, that will cause an increase in heart rate. And if we have a decrease in our threshold, that will also increase our heart rate. So that's our first one. Then we have our muscarinic. And so that could be broken off into two. So we have our beta gamma heterodimer, which will then open up Gurk channels, which will then lower our RMP, which will lower our heart rate. Or we'll have a decrease in camp, which will cause our decrease in HCN, which will decrease our heart rate, or we'll have our L type, or sorry, then this will increase our threshold, which will then decrease our heart rate. And then we have our contractile. And so we'll have epinephrine and norepinephrine that will activate our beta 1. And that will go to our alpha subunit. And then we'll have adenylyl cyclase, which will increase CAMP, which will then activate protein kinase A, which phosphorylates everything, and then it'll be broken into 4 categories. So we'll have troponin, or for proteins, troponin, then we'll have our R, YRCH, phospholambin, and our L type calcium channel. And so this makes troponin. If we do troponin, if you remember, we have our 3 different components, our TIC, and so this will make our calcium, if it's phosphorylated, it'll make this calcium fall off faster, and then that will cause an increase in our inotropy. And then our RYCH, that will more likely to open. That will cause an increase in our calcium concentration, which will then increase our lusotropy. And then our phospholambin, that will increase our circuit pumps, which will then decrease our calcium concentration, and then that will increase our inotropy. And our L type will also be more likely to open. Then that will cause an increase in our calcium concentration, and that will cause an increase in lusotropy as well. And one thing to mention here too is our alpha subunit, if it doesn't get phosphorylated, it could still do the L type calcium channels. This is just, it's more likely for this adenyl, or for this to get phosphorylated, so then it'll kind of go down into here, and then it'll still increase our lusotropy, which lusotropy is our relaxation, and our inotropy is our contraction of the heart for our contractile cells. And that sums up that part of the essay. Okay, real quick, there was a couple things that I missed while doing this. And so before we can decrease our CAM for the muscarinic, I forgot that we still have to activate our alpha subunit. And so I'm just going to draw that right here. So that's going to decrease, so then our CAM can decrease as well. And then down here, I got these mixed up. And so this is going to be an increase in our lusotropy. And this is going to be an increase in our inotropy. This is going to be an increase in lusotropy. And then this is going to be an increase in inotropy. And that fixes those mistakes. For this next and final part of this essay, we're going to talk about the cardiac cycle. And so to do this, I'm going to draw a couple graphs in one. And so I'm going to draw this line here. And this is all for the left ventricle and just the left side of our heart. And so we're going to have pressure, and then volume, and then the sound that it correlates with. So pressure, we have 120, 80, and then about 10. And for volume, we have 120, and then 60. And so to kind of help us keep track of everything, we're going to color coordinate it. So we'll have our left ventricle, our left atrium, and then our aorta. And so to begin, I'll just draw our left atrium. And so we go, and then I'll have this little bump here, and then we'll just keep going and have another little bump and then keep going. And then since blood flows from high to low, to begin, the ventricle is going to have a little less pressure than the atrium, and it's going to just follow the same path. But then here it goes, and then it'll exceed the pressure of the atrium, and it'll get shot up until it hits like 120, and then it'll drop back down and go back below the atrium. And the aorta already has a pretty high pressure, so it's going to be around 80, and it's going to go, and then it's going to go up here, and then it's going to kind of go out. Then it has this little notch, and then it's going to go back down to 80. So that's a little bit about what's happening. And so I'll draw this heart. We got our valve and then our aorta. And so we have the blood flowing from the atrium into the ventricle, then the pressure, and then it goes up into the aorta and then out to the rest of the body. And so what are the different parts of this graph? So right here at this part, we have our mitral valve opening. And then over on this side, we have our mitral valve closing. And then up here at this point, we have our semilunar closes, and then our semilunar opens. And then we have this little section. I should have drawn this little, but like right in here we have our so up here we have our isovolumic contraction and our isovolumic relaxation. And those play an important role in the volume. So when it's contracting, we're going to have our highest volume. So I'm just going to draw a little, and it kind of plateaus. And then for a relaxation, it kind of plateaus at where it has the least amount of volume at 60. So then we could just kind of connect the dots here. So it goes, and then it'll drop down to 60, and then go back up and start over the cycle again. So now we have sounds. So if we go down where also the isolated contraction, that phase occurs, we'll have our first sound, and that will be our lub. And then when we have the relaxation, that will be our dub. And that sums up the cardiac cycle.